A programmable system uses a sequence of instructions to control its operation, as we have seen till now. The instructions that we are going to consider should have some typical specifications, such as the operation to be performed. What do we want to do? Let's say perform an addition or a shift operation, for example. They need to specify the operands to use. When we want to add R1 to R2, for example, or shift left the content of R3, we need to specify the operands and where to place the result or which instruction to execute next. They are also specified by the instruction. The instructions are stored in the RAM, instruction RAM that we have seen, or in the ROM as a program. Okay, so they might also be stored in the ROM. The addresses for the instruction is in a computer are provided by the program counter or the PC that we had already discussed. The program counter's content will be either incremented where we have the count up, or it will be loaded with a new address which is based on an instruction. And usually it could also depend on the status information. Yeah, these are what we will discuss later about the jump and the branch instructions. And then when we say that an instruction is being executed, it means that the necessary sequence of operations specified by the instruction are being activated. For our instruction set architecture, we need to have some resources. The storage resources are visible to the programmer at the lowest software level, let's say an assembly language. Over here you can see the storage resources for the simple computer. We are going to use the Harvard architecture, which means that we are going to have a separate instruction memory and a separate data memory. And as already mentioned, this will let us use of a single cycle for the instruction implementation, because we can take an instruction and we can refer to a piece of data at the same time, because they are located in separate memory units. We also have the program counter and the register file. For our simple computer that we are going to consider, the registers that we are going to use have 16 bits, so 2 bytes. We are going to use 16-bit registers. In our register file, we have 8 of them. So R0, R1 to R7. And obviously, in order to be able to refer to them, we would need to have an address of 3 bits, starting with 000, going up to 111. So 3 bits of address would be enough in order to refer to our register files. For our memory units, we also have the elements of 16 bits or 2 bytes, so similar to the register that we have here, and our program counter will also have the same bits. So as we just mentioned, the instruction which is going to be stored inside the instruction memory consists of a bit vector, so 16 bits in our case for our example, and the fields of an instruction are subvectors representing specific functions and having specific binary codes. So basically we are going to divide these 16 bits that we have for our instruction into some subfields. The subfields may have a given number of the bits, as we will see later, and indeed the format of an instruction will define the subvectors and the function that they have. Usually for ISA we have multiple formats. It's not a single format, so we may have let's say different ways in which the instruction vector, the bit vector, is divided. For the simple computer that we are going to consider, we will have three formats which are going to be presented in the next slides. Over here you can see the three formats. The first format is what we call as register, the second one is immediate, and the third one is jump and branch. So these are the three formats that we have for our ISA. You can see that for all the cases, for all three formats, we have the OP code, the operation code, which determines what operation to be performed. You can see that it spans bits starting from position 9 through 15, and it's common for all three cases. However, the other fields that we have here might be different. Yeah, for example, in the case of register and jump and branch, you can see that they are completely different, even though for all three formats we have 3 bits for each section. So 3 bits here, 3 bits here, and 3 bits here. This determines indeed, and then we have 9 here, so 7 bits will remain for the OP code. In total we have 16 bits in it. Yeah. So let's have a look at the details of each format. The first one that we have is called the register. For the register, apart from the operation code that we have, the next 3 fields that we have are called as destination register DA, source register A, and source register B. For the operations that we have, we might need to have a single source or 2 sources. Okay, it would depend on the operation. Over here you can see an example. In the first example, we have 2 sources. So this is one source, first source, and this is the second source. We have 2 sources and 1 destination. So for the register operations, we have always a destination, but in this case we have a single source for the second example. You can see that all the fields that we have for DR, SA, and SB have 3 bits. So we have 3-bit register fields for all 3. Destination register determines the destination or where the result of the operation should be stored. And since we have 3 bits, we can address any register from R0 to R7. And keep in mind that in our example, we also have 8. Our register file has 8 registers. Yeah. SA specifies the A source register. Again, it could go from R0 to R7. And similarly for SB, the source B, it also determines the second source. So for some operations, we need 2 sources. For some others, we need a single source. For the example that we have here, for shifting operations, which requires a single register, it will be stored in source B instead of source A. And the reason for that is that for the shifter in our data path, we have passed the data coming from bus B into the shift register rather than bus A. That's why we have source B for that. But for the other operations, like incrementing, for example, we will have the destination register giving us the source register indeed. The next format to consider is the immediate. In the case of immediate, we again have the OP code part here. Then we have the destination register similar to what we had. The source register similar to what we had for the register format, but the last field will be different, and it is called OP or operand. This format is used when we have some constant value in our operations. You can see the example here. We want to add 3, which is a constant value, to our R2 register and then store the result in R1. R1 will be the destination register. R2 will be source A, and 3 will be what we have for operand or OP. So basically the source B register field is replaced by an operand field, OP, which specifies a constant. And since we have 3 bits here, so we can go from 0, 0, 0 to 1, 1, 1, or from 0 up to 7. So 7 will be the maximum value that we can have as a constant for our operations. But however, since our register's width is 16 bits or 2 bytes, the rest of the constant value will be filled by 0. So we will have all 0, and then the last 3 bits will come from here, or our OP field of the instruction of the instruction format that we have. The last instruction format that we have is called jump and branch. It is used in order to determine for the program content that it needs to load its content by some new value. Similar to the previous ones, it has the OP code, but now all the remaining fields are different than the other two that we just considered. We have the address left and address right fields, as you can see here. So later these will be combined with each other. And then we have the source register, which will be needed for some operations. So this instruction format supports changes in the sequence of instruction execution, by adding an extended 6-bit signed 2's complement address offset to the PC. Okay, so we will have signed value. It will have 6 bits. The 6 bits that we have here, they will come from the address left, AD left, and address right. So basically these 3 bits will be here, and these 3 bits will be here, and these two combined together will give us 6 bits. So here we have 6 bits in the signed 2's complement. We will have positive values, negative values. For the positive ones, the most significant bit will be 0. For the negative ones, it will be 1. And you are familiar with the signed 2's format, And that will give us the offset, the address offset for our program counter value, or for our PC counter. Here we have an example. Suppose that we have a jump, which is specified by the OP code, and the PC contains initially 45. It has 16 bits, 45 is like this, and then the address that we have contains -12. This -12 comes from our instruction. So here we have 3 bits. Over here we have OP code, which determines the jump. And then the content that we have here is like this, 110, 100. Okay, and since we have the jump instruction over here, which has its specific indeed code, as we will see later, examples later, in this case, what we have for the source A will not be important. But when we have the jump instruction with these values for the address, if you combine them, we will get -12. This -12 will be added to the current value that we have for the program counter, and then the next place that the program counter will point will be obtained as 33. Source A will be used when we have the branches or jumps on the negative or 0. In those cases, the instruction will refer to the source register A, and then if it is negative, or if you have the negative or 0 conditions satisfied, then the branching or jumping will be performed.